Welcome to yet another online course, second one this term. This course will be about exact equations, which are yet another type of first-order ordinary differential equations that can be solved by integration, that is, by quadratures. Traditionally, exact equations are written in differential form, that is, p dx plus q dy is equal to 0. So we have some coefficient which may depend on x and y times dx plus another coefficient which can also depend on x and y times dy is equal to 0. X is the variable and y is the unknown function. So y is a function of x and it is the function we are trying to compute. Formally, if we divide by dx, then this equation is equivalent to p times nothing plus q times y prime is equal to 0. So we can also write it in the usual notation, but the differential form is more traditional. This equation will be exact if there exists some differentiable function of two variables, x and y. The function is denoted by capital F usually, such that the derivative of capital F with respect to x is p, and the derivative of capital F with respect to y is q. So partial f over partial x is the coefficient of dx in the equation, and partial f over partial y is the coefficient of dy in the equation. This function, capital F, is essential to solving the equation, and it is called the prime integral or a prime integral or a primitive of the exact equation. Or it can also be called an integral of the equation. The prime integral is not unique because if you take a prime integral and you add a constant to it, then you get another prime integral, because the derivative of a constant will be 0 either with respect to x or with respect to y. So you can add any constant and it will still have the same property. If an ordinary differential equation is exact, then finding its prime integral is almost the same as finding the solution, because the general solution of the equation in implicit form is given by capital F, that is the prime integral, of x and y is equal to a constant. For any constant, this is a solution of the equation. Any solution of the equation is f of x and y is equal to a constant. Sometimes we have to stop here because this equation f of x and y is equal to a constant may be too complicated to solve, but if it is not too complicated, then we can solve this and find the explicit solution, y of x. Y of x is equal to whatever we get by solving this equation. If not, we leave it like this. This is called the solution in implicit form. Here is the first example. Let's consider the equation y dx plus x dy is equal to 0. This is written in differential form. If we were to divide by dx formally, then we'll get the equivalent equation in standard form, y plus x y prime is equal to 0. Either way, the equation is exact. We don't know this, we don't know how to prove this yet, but we notice that this equation actually has an almost obvious prime integral. Namely, let's try f of x and y is equal to x times y. Then the derivative of x times y with respect to x is y, and the derivative of x times y with respect to y is x. I'm talking about partial derivatives here. So either way, this works as a prime integral, so since it fits the definition, it is a prime integral for the equation. Of course, this is only unique up to a constant, because if we add any constant to x times y, for example, if we take f of x and y is equal to xy plus 11, then this is also a prime integral, or xy minus 20, anything xy plus any constant will work. Since we know the prime integral, then this almost means we know how to solve the equation, because the general solution of this ordinary differential equation then is f of x and y, which is x times y, is equal to a constant. So all solutions of the equation are of this form: x times y of x is equal to a constant. In this case, we can very easily solve for y of x, and we get that y of x is equal to that constant divided by x. This equation is also separable. I invite you to do the computations for yourselves, and you can find out that y prime is equal to minus y over x. And this is clearly separable because minus y over x is the product of a function of x, 1 over x, and a function of y minus y. This is not a coincidence. It actually turns out that every separable equation is also exact. However, separable equations, which we know are separable, are even easier to solve than general exact equations. So this is a particularly important subtype that's easier to solve than the general case. So how do we solve exact ordinary differential equation? And more importantly, how do we know that it is exact? The first step is that we must check that the equation is exact, and there is a criterion which guarantees that it is. And the second step is we need to actually find the prime integral f, and that's almost 90% of the way to finding the solution itself. This is the criterion which ensures that an equation is exact. So let's start with an ordinary differential equation written traditionally in differential form: p of x and y dx plus q of x and y dy is equal to 0. This equation is exact, or to be more precise, locally exact, if and only if partial p over partial y is equal to partial q over partial x. So the derivative of p with respect to y is equal to the derivative of q with respect to x. The proof will be later in this course. And let's just notice that p is the coefficient of dx, but we take its derivative with respect to y, and q is the coefficient of dy, and we take its derivative with respect to the opposite variable, so partial q over partial x. So this works crosswise. P is the coefficient of x dx, and q is the coefficient of dy, but we take the opposite derivatives and we check whether they are equal. This is the criterion. So let's check how this works for a specific equation. For an example, let's consider the ordinary differential equation: x squared plus 2xy times dx plus x squared minus e to the y times dy is equal to 0. Let's check whether it is exact. It is, because the coefficient of dx is p of x and y is x squared plus 2xy, and its partial derivative with respect to y is just 2x, right? X squared doesn't contribute, it's just a function of x. And so we have just the partial derivative of 2xy with respect to y, which gives 2x. And the coefficient of dy is q of x and y, which is x squared minus e to the y, and its partial derivative with respect to x is again 2x, because now we are taking partial derivatives with respect to x, so minus e to the y doesn't contribute, and we just have the derivative of x squared, which is 2x. And they are equal, so both of them are 2x, And then by the criterion stated on the previous page, this means that the equation is actually exact. Once we find that an equation is exact, then we can proceed with solving it by computing its prime integral. If the equation is not exact, then none of these methods I'm about to describe applies, of course. These only work for exact equations. Now, there are three usual methods that are used for solving exact equations. Let's have a look at all three. So the most straightforward one is we compute the line integral of p dx plus q dy, except that I'm using some different variable names because I'm computing this integral from a fixed starting point x0, y0 to the point xy where we're computing f of x and y. So I'm going to give x and y new names under the integral. X will be u and y will be v. So this is integral of p of u and v du plus q of u and v dv. This is a line integral, so it's supposed to be computed along some path from the point x0, y0 to the point xy. Now it turns out that if the equation is exact, then it doesn't matter what path we choose between the 2 points. But let's have a look at that. As an observation, the path that we choose must be inside the domains of definition of the functions p of x and y and q of x and y. If these functions are defined, for example, on the whole plane, then we can choose literally any path from the fixed starting point to the point xy. If not, then choosing a path becomes more complicated, and it turns out that the answer may actually depend on the path, which is not good. So if the criterion for exactness partial p over partial y is equal to partial q over partial x is fulfilled, then the equation is exact and the line integral only depends on the endpoints, not on the actual path. In order for this to happen, also the domain must have a sufficiently nice and simple shape. Otherwise, we get an answer that depends on the path, which is wrong because f of x and y is supposed to only depend on x and y, not on the path. And it's not going to depend on the starting point because we fix the starting point once and forever. But supposing that we chose a different starting point and we did the same computation, then this is also going to give a prime integral for the equation. Since both of them are prime integrals for the same equation, then they must be different by a constant. So if we choose a different starting point, we have to obtain the same answer that we obtain for the first starting point plus a constant. So the choice of starting point doesn't matter, it just gives the same answer up to a constant. So let's return to our previous example, which is x squared plus 2xy dx plus x squared minus y squared minus e to the y dy is equal to 0. And let's recheck that it is exact. So again, p is x squared plus 2xy. So its partial derivative with respect to y is 2x. Q is x squared minus e to the y. Its partial derivative with respect to x now is again 2x, and they're equal. Therefore, the equation is exact. Well, if the equation is exact, then we can always compute the prime integral by the same formula. Like I said, it's going to be given by a line integral from some fixed starting point to the point xy, of coordinates xy, where we are computing the prime integral. And there is no simpler choice for the starting point if we are allowed to make any choice than the point of coordinates 0, 0. So let's make this choice. Let's start our line integral at the point 0, 0. So then we have integral from the point of coordinates 0, 0 to the point of coordinates x, y of p of u v du plus q of u v dv. So let's replace them by what they are. P is the coefficient of dx, so it's going to be u squared plus 2uv, and q is the coefficient of dy, so it's going to be u squared minus e to the v. And now, as I said, if these functions are defined on the whole plane, then we are allowed to choose any path in between the point 0, 0 and the point xy. So let's again make a very simple choice. Let's make a path. We could make a straight line path, but this is even simpler. We make a path from two segments. We first go horizontally from the point of coordinates 0, 0 to the point of coordinates x0, and then we go vertically from the point of coordinates x0 to the point of coordinates xy. And this makes the computation very simple. So again, this path integral now becomes the sum of the integrals along these two line segments. And the first line segment is completely horizontal. So this means that the dv portion does not contribute because dv is the vertical coordinate, so it's not going to contribute along a horizontal segment. So then we are just left with the integral of u squared plus 2uv du along the first segment. And even better, along this first segment, the second coordinate is 0 because we are integrating from 0, 0 to x0. So the second coordinate is always 0. So this means that v is 0. So we just have integral of u squared plus 2u times 0 du, so which just means integral of u squared du. Now for the other segment, for the vertical segment, well, along this segment, the du portion will not contribute anything because du refers to the horizontal coordinate. So we're just left with the dv portion. So we have the integral of u squared minus e to the v dv. And u along this segment is constantly equal to x because we start from x0 and we end up at xy. So then under the integral, we are just going to have x squared instead of u squared minus e to the v dv. So by choosing this path made of two line segments, one horizontal line segment and one vertical line segment, the computation is actually very straightforward. We have to compute the integral of u squared du, which is going to be u cubed over 3, and this is evaluated between 0 and x. So this is x cubed over 3. And then for the second integral of x squared dv is x squared times v, and that's evaluated between v equals 0 and v equal y. So this gives x squared times y. And then the integral of minus e to the v is, again, minus e to the v. And this is evaluated between 0 and y. So this is 1 minus e to the y, where 1 is e to the 0, or whatever. So this is our prime integral. It's x cubed over 3 plus x squared y plus 1 minus e to the y. So if we know how to compute line integrals, then this is a straightforward way of computing prime integrals for these exact equations. And then, as promised, this is 90% of having the solution to the equation. Now we have the implicit solution to the equation is x cubed over 3 plus x squared y plus 1 minus e to the y is equal to some constant, which I call C1. But then notice that I have two constants. I have 1 on the left-hand side and I have C1 on the right-hand side. So let's subtract 1 from C1. And we should have x cubed over 3 plus x squared y minus e to the y is equal to C2, please remember. Notice that this equation is too complicated for us to solve for y. I mean, we really don't have a method for solving this type of equations, except numerically. As for x, we could solve it for x as a function of y if we wanted. And then we would need how to know how to solve cubic equations. The next method, and the one that I prefer, is in order to find a prime integral capital F for an exact equation. So in order to solve these two equations, partial f over partial x is equal to p and partial f over partial y is equal to q, well, instead of using the line integral, we can actually solve these two equations one equation at a time. So first we solve the first equation, partial f over partial x is equal to p. So we integrate both sides of the equation as a function of x. The integral of partial f over partial x is f itself. And then the integral of p is something that we can compute, integral of p of x and y dx. The thing is that when we integrate as a function of x, we actually perform one separate integration for each value of y, and therefore the constant of integration that we get will depend on y. So it's not really a constant, it's a function of y, c of y. It's one individual value for each y, so it's a function of y. And in these integrals, as I said, we integrate separately for each value of y, and this allows us to treat y as if it were a constant. So for example, the integral of xy dx in this context is just x squared over 2 times y plus a constant that depends on y, because we treat y as a constant. So the integral of x times a constant is x squared over 2 times that constant. Or let's see, integral of e to the x times e to the y will again be e to the x times e to the y. No, let's see, integral of e to the 2x times e to the y will be e to the 2x over 2 times e to the y. So in all of these, we treat y as if it were a constant number. So now we solve the first equation by integrating in x, and we get that f of x and y is equal to integral of p of x and y dx plus c of y. So this is a valid formula for f. It's a true formula, and we have almost solved the problem, except that we don't know what c of y is. So that's why we need to take this formula for f and plug it into the second equation. So the second equation was partial f over partial y is equal to q. So this means the derivative with respect to y of f, and we let f be given by this formula. So partial over partial y of integral of p of x and y dx plus c of y is equal to q. And now when we take this derivative with respect to y, we get partial over partial y of this integral, which is something that we can compute, plus c prime of y, because c is a function just of y, so this is an ordinary derivative, it's not a partial derivative, c prime of y, and then is equal to q. And from all this, we're interested to compute, we want to compute c prime of y, so that we can then compute c of y itself. So from this equation, we get that c prime of y is q minus partial over partial y of this integral. So we have that c prime of y is q minus partial over partial y of integral of p of x and y dx. And here is where it measures that the equation is exact. So if the exactness criterion partial p over partial y is equal to partial q over partial x is fulfilled, then the right side of the equation will not depend on x at all. It will just be a function of y. And then we have c prime of y is equal to this complicated looking function of y. And then we just integrate with respect to y. and we get that c of y is equal to integral of this expression dy. When we do this, sometimes we get that c of y is an actual constant, but usually we just get some function of y. And then knowing this function of y, we replace it in the original formula of f, and this is our prime integral. So here is an example. We have the equation x squared plus 2xy dx plus x squared minus e to the y dy is equal to 0. Well, this is the example we have solved already, and we know it is exact. Now let us use a different method to solve it, just for comparison. So again here, p of x and y is x squared plus 2xy, and q of xy is equal to x squared minus e to the y. And we have two equations for the prime integral. Partial f over partial x is equal to p, and partial f over partial y is equal to q. So let's start with the first equation, and we have partial f over partial x is equal to p. This means that f is equal to the integral of p. So f of x and y is equal to integral of x squared plus 2xy dx plus this constant, which is actually not a constant, it's a function c of y. Well, the integral of x squared is x cubed over 3, and the integral of 2xy is x squared y. So we get a formula for f of x and y. It's x cubed over 3 plus x squared y plus c of y. And then we'll use the second equation to find c of y. So the second equation is partial f over partial y is equal to q, and we have our formula for f already, namely x cubed over 3 plus x squared y plus c of y. So we plug that into the equation instead of f, and we get that partial over partial y of this formula for f is equal to q, which is given, it's x squared minus e to the y. And then what is partial over partial y of this parenthesis? X cubed over 3 doesn't contribute anything. The derivative of x squared y with respect to y is just x squared, and the derivative of c is c prime. So x squared plus c prime is equal to x squared minus e to the y. Well, the x squared cancels, and we get that c prime of y is minus e to the y. So this is where it measures, as I said, that the equation is exact. If the equation wasn't exact, then we could get something like c prime of y is equal to x squared plus y squared, or something illogical like this, which we couldn't solve because c can only be a function of y. So there shouldn't be any x once we get to this stage. Just c prime of y is equal to a function of y. And well, let's see. So since c prime of y is minus e to the y, this means that c of y is equal to the antiderivative of minus e to the y, which is itself, because the antiderivative of e to the y is itself. So we get c of y is minus e to the y, maybe plus a constant. So the prime integral is x cubed over 3 plus x squared y plus c of y, and we replace c of y by minus e to the y plus c. So we get x cubed over 3 plus x squared y minus e to the y plus c. And now that we know the prime integral, this means the solution is the prime integral f of x and y is equal to a constant. So x cubed over 3 plus x squared y minus e to the y plus c is equal to some other constant. And of course, again, we can take the difference of the two constants and leave it on the other side. And we have x cubed over 3 plus x squared y minus e to the y is equal to c2, where c2 is the difference of the previous two constants. So the answer is the same. Finally, this is the third method, and I don't recommend using it unless you know what you're doing, because even though it's much easier, you could make mistakes in the computation. So again, we want to find the prime integral f by solving the system of equations. Partial f over partial x is equal to p, which is the coefficient of dx in the original equation, and partial f over partial y is equal to q, which is the coefficient of dy in the original equation. So in order to do that, we solve both of these equations. Partial f over partial x is equal to p, and partial f over partial y is equal to q at the same time, and then we match the terms that we get. So to solve the first one, we get f is equal to integral of p of x and y dx, and to solve the second one, we get f is equal to integral of q of x and y dy. And then we examine the terms that we get from both integrals, and the prime integral will be the sum of all these terms that appear in either integral, but we only write those terms that appear in both integrals once. So when writing the sum, if there is a term that's present both in the first integral and in the second integral, we only write it once. Now let's solve the same equation again by this third method for comparison. So the equation is the same one. We know it is exact. The equation is x squared plus 2xy times dx plus x squared minus e to the y times dy is equal to 0. So now we compute both integral of p dx and integral of q dy, where p is the coefficient of dx, so p is x squared plus 2xy, and q is the coefficient of dy, so it's x squared minus e to the y. Then integral of p dx is, well, let's compute it. It's x squared plus 2xy. So the integral of x squared is x cubed over 3. The integral of 2xy is x squared times y. What about q? We didn't do this computation before. So q is x squared minus e to the y. The integral of x squared, so we treat x as a constant. So x squared is a constant. So the integral of x squared is x squared times y, just as if, let's say, x squared were a number like 9, its integral would be 9y. And the integral of minus e to the y is minus e to the y. So I get x squared y minus e to the y, maybe plus a constant. So then what are the terms that we get? We get x cubed over 3, x squared y again from the second integral as well, and minus e to the y. But as I said, if a term appears both in the first and in the second integral, then we only write it once. So the prime integral will be x cubed over 3 plus x squared y times only one of them, and then minus e to the y. And again, this is the same answer that we got by the other two methods. So these are three of the most usual methods for solving exact equations. In either case, we should first check whether the equation is exact. That is the first step. And then, if you like line integrals, you can compute line integrals. If not, you can do integrations, like in the other two methods. And in either case, by following the method, you obtain the prime integral. And the solution is f of x and y is equal to a constant. This is the implicit solution. And then if you can solve for y, then you get y is equal to some function. That's the explicit solution. We'll do more examples next time. But until then, let's have a little look at the theory behind exact equations. So first, a word. Why are exact equations called exact? Where does the name come from? Well, if you have a function of several variables, like here capital F of x1, x2 up to xn, then the differential of such a function is defined as d capital F is equal to sum of its partial derivatives over each variable, d that variable. So partial f over partial x1 dx1 plus partial f over partial x2 dx2, and so on and so forth up to the last variable. So in particular, for a function of two variables, f of x and y, this differential is df is partial f over partial x dx plus partial f over partial y dy. And then we notice that an equation, an ordinary differential equation, p dx plus q dy is equal to 0 is exact if and only if this whole equation, or the whole left-hand side of the equation, is exactly the differential of some function capital F, which is the prime integral. So df is p dx plus q dy. This is what it means that partial f over partial x is equal to p, and partial f over partial y is equal to q. So exactly when this happens, then df is p dx plus q dy. So this is why exact equations are called exact, because the left-hand side in an exact equation is exactly the differential of some function f of x and y, which is the prime integral of the equation. This is what gives the name to the exact equations. Yes. This is the first theorem that we need in the study of exact equations. It says, if we have a prime integral for the equation, then this can be used to find every solution. The theorem says the following: consider the exact ordinary differential equation p dx plus q dy is equal to 0, where p and q are functions of x and y. And suppose that this has a prime integral capital F, meaning that partial f over partial x is p, and partial f over partial y is q. Then the general solution of the equation in implicit form is capital F of x and the unknown function y of x is equal to a constant. Here, capital F again is a prime integral. Well, so again, this theorem justifies why we look for prime integrals when we deal with exact equations. All right, so now let's prove this theorem. The proof will have two parts. In the first part, we're going to consider a solution of the ordinary differential equation, y of x, and we're going to prove that f of x and y of x is a constant, where f is our prime integral. And in the second part, we're going to assume that y is some function, we don't know whether it's a solution or not, such that capital F of x and y of x is a constant, and we're going to prove that y actually is a solution. This will be on the next page. So in the statement of the theorem, we are given the equation p of x y dx plus q of x y dy is equal to 0, but it's better to write it for this proof in the standard way instead of differential notation. So we divide the equation by dx and we get p of x and y plus q of x and y times dy over dx, which is the same as y prime, is equal to 0. And now let's assume that y of x is a solution of the equation, and let's take capital F to be a prime integral. Capital F being a prime integral means partial f over partial x is p, and partial f over partial y is q. Okay, so now let's form this expression that we want to know whether it's a constant or not. So capital F of x and y of x. We have replaced the variable y by the function y of x. So now everything here is a function of x. So we have capital F of x and y of x. It's just a function of x. So now let's take its derivative as a function of x. And we get the derivative of f of x and y of x is by the chain rule. So it's going to be partial f over partial x times dx over dx. This is from just from x as an argument, and then plus partial f over partial y times dy over dx. This is from the second argument, which we replaced by y of x. But partial f over partial x is just p. Dx over dx is 1. So this just means the derivative of x as a function of itself. So x prime, that's 1. And dy over dx is nothing but y prime. So we get that the derivative of the whole expression is p plus q times y prime. But we know that this is 0 because if y is a solution of the equation, that's exactly what it means. It means that p plus q times y prime is equal to 0. So now this expression, f of x and y of x, was only a function of x. And we have proved that its derivative as a function of x is 0, and therefore it is a constant. Because a function whose derivative is 0 must be a constant. So now in the second part, we are not going to assume that y is a solution. We just take some function y of x such that capital F of x and y of x is a constant. And we want to prove that y of x is a solution. So we start with this equality, f of x and y of x is a constant, and we take the derivative of both sides with respect to x. The derivative of the constant with respect to x must be 0 because the derivative of a constant is 0. And on the other hand, this must be equal to the derivative of f of x and y of x. Again, we compute this derivative by the chain rule. So it's partial f over partial x times dx over dx plus partial f over partial y times dy over dx. And then this is equal to partial f over partial x is p, partial f over partial y is q, and then dx over dx is 1, and dy over dx is the derivative of y with respect to x. So let's write it as y prime. So we get that the whole thing is p plus q times y prime. But at the same time, we know that it's 0 because the derivative of the constant is 0. So we get that p plus q times y prime is 0. But this is exactly what it means that the function y is a solution of the equation, because this is the equation. P plus q times y prime is equal to 0. And if we multiply by dx, we can also write it in differential form, and then it looks like the equation we had in the beginning. P dx plus q dy is equal to 0. So the second theorem that I want to briefly prove here is that the criterion that we use for exactness actually works. So consider an ordinary differential equation, m of x and y dx plus n of x and y dy is equal to 0. So this is written in differential form. And suppose that capital M and capital N are continuous and continuously differentiable functions on some region, on some rectangular region, where x is between a and b and y is between c and d. So this is a rectangular region in the plane. Then the ordinary differential equation is exact on this region, if and only if the criterion we have used is true. So partial m over partial y is equal to partial n over partial x. The proof of the exactness criterion, I guess, has two parts. First, we assume that the equation is exact and prove that the criterion must be true. And then on the next page, we'll assume that the criterion is true and we'll prove that the equation must be exact. So for the first part, if the equation is exact, then by the definition of exactness, this means there exists some prime integral, capital F of x and y, such that in the equation, the coefficient of dx, which is m, is given by partial f over partial y, and the coefficient of dy, which is n, is given by partial f over partial y. Then partial m over partial y is, well, what is m? So m is partial f over partial x. And then partial m over partial y is going to be the derivative with respect to y of partial f over partial x. So this is the second order partial derivative, partial square f over partial y partial x. And in the same manner, what is partial n over partial x? Well, it is the derivative with respect to x of partial f over partial y. So this is the second order, the mixed partial derivative, partial square f over partial x partial y. But then you know that these second order mixed partial derivatives are equal to each other because, well, it doesn't matter in what order you take the derivative. Either you take it first with respect to x and then with respect to y, or first with respect to y and then with respect to x. And there's a theorem that tells that they are equal. It's called Clairaut's theorem. And it says that if all the second order partial derivatives of capital F are continuous, then the mixed partial derivatives, partial square f over partial y partial x and partial square f over partial x partial y, must be equal to each other. So indeed, partial m over partial y is equal to partial n over partial x, because each of them is one of these mixed partial derivatives, and they are equal to each other. Now I'm only going to sketch the converse of this. So now we assume that this exactness criterion is satisfied. So partial n over partial y is equal to partial n over partial x. And we prove that there exists a prime integral. And the way that we do this is, if partial n over partial y is equal to partial n over partial x, then this is exactly the condition that's necessary for the line integral, integral of m dx plus n dy, to be path independent. And then we can define the prime integral by this line integral. So capital F of x and y is equal to the integral from some fixed starting point to x, to the point of coordinates x and y of m du plus m dv, as in our first solution method for exact equations. So this integral, this line integral, is independent of the path, and then one can prove that the function capital F defined by this line integral has the property that partial f over partial x is m, and partial f over partial y is m. So it is a prime integral for the equation. Just one warning. Everything that I have said so far only applies to domains with simple shapes, like rectangular domains, for which I stated the criterion. But more generally, for the whole plane, or for a disk, or for a triangle, in any case, a domain that doesn't have holes in it. For more complicated regions, the criterion is only partly true, namely, if the equation is exact, then it follows that partial n over partial is equal to partial n over partial x. But if the criterion is fulfilled, so if partial n over partial y is equal to partial n over partial x, this is no longer enough to guarantee that the equation is exact on the whole region if it has a complicated shape. What happens instead is that if the criterion is fulfilled, then the equation will be exact on simple regions, on regions with simple shapes inside the overall domain, but it may fail to be exact on the whole region if it has a sufficiently complicated shape. Well, the reason for this is that if the domain of definition, if the region on which we are studying the equation, if the domain of definition of the functions m and n has some holes in it, then the path integrals may give different results according to the number of times you go around those holes. So enough theory for now. In any case, this theory is just to explain why we use this method to solve exact equations. You don't really need to memorize it. Now let's go back to an example. Let's consider the ordinary differential equation 2x plus y dx plus x plus 2y dy is equal to 0. So this is written in differential notation, and if we divide it by dx, we would get the same in standard form, 2x plus y plus x plus 2y times y prime is equal to 0. And now, first, let's check that this equation is exact. So in this equation, p of x and y is 2x plus y, and q of x and y is x plus 2y. And then partial p over partial y is 1, because 2x doesn't contribute. Partial q over partial x is also 1, because 2y doesn't contribute. So since they are equal, they are both 1, this means the equation is exact. And if the equation is exact, then let's try to find its prime integral, or a prime integral. The prime integral will be a function such that partial f over partial x is 2x plus y, and partial f over partial y is x plus 2y. So let's solve these two equations one at a time. This is the second method that I introduced in this course. We start from the first equation, partial f over partial x is equal to 2x plus 1. So that's the coefficient of dx, or p. And then when we integrate this as a function of x, we get f is equal to integral of 2x plus y dx. Well, integral of 2x is x squared, integral of y is x times y, and then it's plus c of y. So it should be a constant, but it actually is a function of y. So the next step is to find c of y by plugging this formula for f in the second equation. So we know that f of x and y is x squared plus xy plus c of y. When we plug this into the second equation, partial f over partial y is x plus 2y. So when I take the derivative of this expression as a function of y, x squared doesn't contribute anything. Xy, well, we get an x, because the derivative of xy with respect to y is x. And then the derivative of c of y is c prime of y. So we get x plus c prime of y. And this is equal to x plus 2y. Well, the x cancels, and we get that c prime of y is equal to 2y. And here again, this is because the equation is exact, that we get that c prime of y is only a function of y, as it should be. If the equation were not exact, then maybe we would get some stranger terms here, like we could get c prime of y is equal to x times y, and then we wouldn't be able to solve the equation by this method because it wouldn't be exact. So here we get c prime of y is equal to 2y, so then clearly c of y is the antiderivative of 2y. So it's y squared plus a constant. And then our prime integral is x squared plus xy plus, and we replace c of y by y squared plus a constant. And we can even take that constant to be 0 if we want, and we get that the prime integral is just x squared plus xy plus y squared. And the solution is x squared plus xy plus y squared is equal to a constant. Now, this is the solution in implicit form, and finally, we have an equation for which we can go further and solve this equation for y. Notice that this is a quadratic equation in y. Namely, we can write it as y squared plus xy plus x squared minus c1 is equal to 0. So let's solve it using the quadratic formula, and we get that y of x is equal to minus x plus or minus x squared minus 4 times x squared minus c1, everything divided by 2. Well, you can check for yourselves using the quadratic formula. And I want to say that even though in this formula we have plus or minus, actually for each individual solution, it will be always plus or always minus, because otherwise we would have a jump on the discontinuity for y of x, which must be continuous. So each individual solution is either minus x plus the square root or minus x minus the square root. And this is it for this example. We'll continue with more examples in the next course. Thank you again for your attention.